Hi, everyone. I'm Pradeep Natarajan, Senior Principal Scientist at Amazon Alexa AI. Today, I'm going to talk about error detection in large-scale conversational assistants through offline models. To quickly introduce Alexa to you folks and the systems underlying it, there are 5 key components to Alexa: the wake word detection, the automatic speech recognition, the natural language understanding module, the text to speech, which outputs the response, and then the Alexa voice service that allows developers to build skills and experiences that leverage all of these other technologies. So if you look at the sequence of modules that are invoked when you go and talk to your Alexa device, say you say something like, Alexa, play Bad by Michael Jackson. What happens is there is a wake word model running on device that's listening for the word Alexa. And as soon as that model triggers, it captures the audio and invokes the conversational assistant. The conversational assistant then calls the automatic speech recognition system that converts the audio stream to text. And then it calls the natural language understanding system that does 2 things. First, it understands the domain and intent of the utterance. For example, that this is a music domain utterance and the intent is play music intent. And then it also recognizes the entities that are named and resolves it to the right entity in our database. For example, the artist name is Michael Jackson and the album name is Bad. And then potentially retrieves the entity from your Spotify playlist or something like that. Once these are done, the next step is to generate the result and then render the result through the text-to-speech module. And that produces the response, playing Bad by Michael Jackson, and then the song gets played. So if you look at the wake word detection model, we have a multi-stage convolutional neural network-based model running on device. For those of you who are from a computer vision background, this architecture looks quite familiar. And then for the automatic speech recognition system, we have models that are essentially outputting multiple different outputs. For example, the language identification, the transcription network that produces the text from the audio stream, and so on and so forth. The natural language understanding model, as we just now discussed, applies a series of models for classifying the question, for generating the answer candidates, ranking the answer candidates, and then passes off the ranked answer to the downstream text-to-speech system. And in terms of generating the answer, we search through multiple databases we have, for example, a knowledge graph, Wikipedia, web documents, so on and so forth. In terms of the text-to-speech, we again have a neural net-based model that takes the output that is generated by our model and then converts it to a audio response that you hear. So if you look at this multi-stage pipeline, what are the possible sources of error? Failures can occur in each stage of the pipeline. Error patterns are often related to specific design and modeling choices we make for these modules. And these errors are also relatively rare and quite difficult to identify in an industry-strength conversational assistant. So I'm going to present 2 use cases in this talk for monitoring and detecting errors in our online system through offline models. The first use case focuses on detecting errors in the domain decoupled NLU model that I'm going to describe next. And the second use case focuses on isolating sources of error, like whether it's the wake word or the ASR or NLU or TTS that resulted in an error in the multi-stage processing pipeline. In both of these cases, we are going to leverage offline transformer-based models to detect errors in the online system. For those of you not from an NLU background, Transformers are among the most performant models that has been used in the community in recent years. They have extremely high accuracy, but they are also typically have large parameter counts that makes them somewhat slow for many online applications. So in terms of detecting and correcting errors in the NLU system, first I want to give you some introduction on how an NLU system is designed and why we make those design choices. So with a large-scale conversational assistant, name it, whether it is Alexa or Siri or Cortana, they all process billions of utterances every week. These utterances are typically partitioned into domains such as music, movies, weather, wiki, etc. And the customer experience and model artifacts for each of these domains are managed by independent teams. So to illustrate, this is how the modularized NLU system looks like. So for example, the books domain will have a domain classification model that can process every utterance and provide a confidence on whether the utterance belongs to that domain or not. Similarly, they also have intent classification models that decides whether an utterance is a read book intent or a find book intent or a buy book intent and so on and so forth. And then there's a named entity recognition model that looks at the sequence of words like play Moana and then identifies which are the named entities, in this case, Moana, and associates a particular named entity type like book name and a confidence for it. Similarly, the music domain has its own domain classification model, intent classification models, named entity recognizers, and so on and so forth. Now, what happens is when an utterance comes to the NLU system after the speech recognition module has processed the audio stream, each of these domains apply their models in parallel, and they generate possible interpretations of the utterance. Next, what happens is a re-ranker takes these interpretations from the different domain models and sorts them in order of confidence, and then produces a list of hypothesis interpretations for across all domains. So this illustrates how the individual domains are generating their hypothesis. And why is this architecture useful? The key is that this allows rapid scaling to support multiple domains, catering to billions of diverse utterances. Domain teams operate independently and update their models asynchronously. So what the book team needs to do to improve their experience is independent of what a music domain might need to do. And they don't have to coordinate and such. Every time they see that there is a problem they want to fix or a new feature they want to provide to the customers, they can quickly go ahead, build their own models, launch it to production, and start serving their customers. So this eliminates any cross-team dependencies and allows for rapid deployment of fixes and new features. But this architecture also creates a unique problem, which is called the domain false route problem. What is the FR problem? An utterance belonging to a particular domain X is instead routed to a different domain Y. So essentially, we misclassify the utterance. And why are these false routes hard to detect? False routes are a small fraction of overall traffic in an industry strength conversational assistant like Alexa. Just to illustrate the challenge, consider a domain X accounting for 0.5% of total traffic, and 20% of this 0.5% are FRs to other domains. That is, these false rejects account for 0.1% of overall traffic. Now, do the math. If you have billions of utterances every week, 0.1% is a very small fraction that you need to identify by sifting through all of that traffic, right? This is a classic needle in the haystack problem. So the solution we developed for identifying these false routes is based on leveraging transformer models. So what we built is a multi-layer processing pipeline that is illustrated in this figure. We take each utterance text that we saw in live traffic and encode it to a specific transformer model called Roberta. In addition, we also take the logs from our production system, like the confidence outputs from the NLU domain models and such, and then embed it into a numerical vector as well. Then what we do is we take the Roberta-based encoding as well as embeddings of the metadata, like confidence scores from the production models, concatenate them, and then feed them into a feed-forward layer with a feed-forward neural net. And then we train this full multi-stage pipeline in an end-to-end way in a multitask setting. So essentially, we are training the model to predict two things. One is a particular utterance a false route? And the second is it in the domain that we are interested in? So these illustrate the results that we were able to get. So we initially had a BiLSTM, which is another language processing model that was popular in the community a few years ago. And then we found that it has an F1 score of about 13.1, fairly low for the particular domain we were building this model for. When we moved to the transformer-based Roberta model, we saw the F1 score improve from 13.1 to 25.2. Then when we included the metadata embeddings, which is what we are calling as NBEST in this table, and trained for the single task of whether classifying a particular utterance as a false route or not, we were able to improve the F1 score further to 28.1. And then when we use the multitask setting I illustrated in the previous figure, we improved further to 30%. And then when we trained multiple such models and then aggregated their joint outputs in an ensemble, we saw a further improvement to 32.2. So overall, through our work, we improved the F1 score from 13.1 to 32.2. This work was published in ACL in 2021. And we did a further deep dive. So if you look at it in row 2, you see a Roberta-based model where we just encode the current utterance and use it to classify, versus all the other additional things we added. So if you look at the F1 scores alone, we improved from 25.2 to 32.2, which is significant. But if you actually dig deeper into the trade-off between precision and recall, we find that the simple Roberta-based model has very high precision initially. That is, it detects a whole bunch of utterances. But as we start lowering the threshold, the recall doesn't go up as much. So essentially, the Roberta-based model was identifying a lot of similar utterances initially, but was not generalizing to a broader set of false routes. But as we started making all the enhancements I just now described, we got a precision recall curve that offered a better precision versus recall trade-off at different operating points. So in terms of production impact, we leveraged the model in a human-in-the-loop offline system for false reject identification. So essentially, we applied our model at a particular operating point, identified utterances that were marked as potential false routes by the model, presented it to humans to verify if they are indeed false routes, and then used those as training examples to improve our production models. We were able to accelerate our annotation throughput by 5 times from the baseline BiLSTM model. In addition, we also reduced false routes in production for the domain we targeted by an absolute 20%. We were also able to scale to multiple languages with minimal architectural languages because Roberta is an inherently multilingual model. So this is a classic example of advances in NLP community having a practical impact in a large-scale system used by millions of users every day. So the next problem we looked at is failure point isolation. Here, going back to the figure I originally showed on the multi-stage pipeline we use to process every utterance, the goal of our work is to identify which of these modules failed first when we see an erroneous response by Alexa, and then dig deeper into the problems that caused that failure. So there are many failure points in a dialogue system. As you know, it could be false wakes, where the device woke up incorrectly. It could be an ASR error, where it produced the wrong transcription of the audio input. It could be a NLU error, maybe domain classification or intent classification, or it could be an entity resolution error, or it could also be an error in the results that were generated by the response generation component. Or finally, which is the vast majority of our utterances, is that we process the utterance correctly. So to illustrate an example of our failure point isolation, consider this figure. So in the first term, the user says open the garage door, but the ASR module incorrectly transcribes it as open the garbage door. The NLU can process it correctly and mark the intent, the domain, as well as the entities correctly. But the entity resolution can't work. But this was not the first failure point. The first failure point was the ASR. And the user gets a defective response where we say, sorry, I couldn't find a door with the name garbage. Now consider the second example, where the user says open the garage door and ASR transcribes it as open garage door, right? The was dropped. So ASR transcription is incorrect, but it's not a failure point because the subsequent system is able to handle it correctly. And the user does not perceive a defect. Now look at the final example. The user asks something like, make me a sandwich. ASR got it right, NLU got it right, entity resolution got it right, but Alexa has to respond saying, sorry, I don't know how to do this. So the user perceives a defect, but there is no failure point in our processing system as well. So these are all different examples that we see in live traffic. So to build a failure point isolation model, we first collected a training data set with 1.5 million user requests that we split into train, dev, and testing datasets. Our dataset also included dialogues in 8 languages and was annotated by a single annotator to identify which point was a failure or if the utterance was processed correctly. We then used this training data set to train our failure point isolation model. In addition, we also collected a golden data set where we annotated 58,000 sessions using multiple annotators, an ensemble of machine learning models as well to verify the annotations. And finally, an expert who looks at the labels from the models as well as annotators to finalize the final label. So this is a much more heavy duty annotation workflow that we classify as the golden data set. And all the results we represent here in this paper, in this presentation, are on this golden data set. This is also used to estimate the performance of a non-expert human annotator. So if you look at the key model components, the figure on your right illustrates what we are doing. So we have 3 independent processing layers. The first is the language model that takes the current utterance, the previous utterance by the user, the next utterance, as well as Alexa's responses, and encodes it in a language model. The second is a set of numerical features that we embed using a neural net model. These numerical features could be confidence scores output by different models in our processing workflow. And the final is our categorical features, like the classifier output saying the domain is a books domain or a shopping domain and the corresponding confidences. We also embed this, and then we concatenate these embeddings and then have a series of mixing layers that produce the final classification output to isolate the failure point. If you look at the results, we see that just from the language model component, we get a 40.3 F1 score. And as we start adding all of these different metadata features, we are able to improve this all the way to 51.4. How does this compare to human performance? If you look at the best model we were able to train after ensembling, we had a 53.5 F1 score, while humans had a F1 score of 57.4. That means that our model-based approach is 92.2% as accurate as our human workflow, right? So overall, to summarize, we presented a novel method for failure point isolation in these large-scale conversational assistants. We did this by training a predictive FPI model that demonstrates performance comparable to humans. We also demonstrated the importance of key model features, and our system achieves 92% of human performance while also scaling to the entire Alexa traffic, while human annotations for billions of utterances is infeasible. What are the key takeaways overall? We presented two techniques for monitoring and detecting errors in a large-scale conversational assistant. The first approach focused on one specific module, namely for natural language understanding. The second approach focused on isolating the failure points in the multi-stage pipeline to process an utterance. Both systems relied on an offline transformer-based model to detect errors in the online system. Our methods are able to scale up to large traffic volumes where human review is infeasible. Thank you very much. We look forward to hearing your feedback.